Hi everyone. I wanted to make this quick video going over some of the calculations for Module 5. I believe it was question 6, which asked you to determine if the dye concentrations that we found at the site of the textile mill were possibly at a level where they might be lethal to some of the fish. And that is a difficult calculation. I'm not going to lie about that. However, it's a calculation that you have the tools to do. At this point in the semester, between both this class and CHY 113, you should have a set of problem-solving skills that would enable you to do a calculation like this. And that's part of the whole idea behind this question, is to test where you are with your ability to problem-solve and think analytically. And so this is not a calculation directly that you have seen at all. And I know some of you were very daunted by it. Some of you looked at that calculation and just said, wow, what is going on there? I have no idea how to even start something like this. My goal by the end of this short video is that you'll see that yes, indeed, you do have the tools to do that it really is just a simple matter of problem solving and thinking about it and thinking about how to approach the question. And so that's not to insult anyone who didn't get it. And if you looked at it and you were just completely daunted, then that's okay too. That happens sometimes. But again, sort of my goal behind this video is to show you that if you sit back and you just think about it for a minute, it honestly really isn't that hard. You just have to apply some real problem solving approaches to this question. And so actually I've got the question right here, don't I? I do, question 6. So assuming that a 2 kilogram fish filters 100 liters of water a day, what is the maximum mass of each dye the fish comes into contact with? Consider the Ld50 value for each dye and explain if the amount of dye is potentially toxic. And so let's think about what we need to know in order to answer that question. The first thing we have to determine was one of your big goals for this module was simply to determine what the actual concentration of the dyes in the river were. And for that, you can see my data here. I ran the data as well. So you had data for a calibration curve for each dye. We identified methyl red and malachite green. And so this was the data that was provided to you in this instance for this semester. In a normal semester, you would have gathered this data and created your own curve. But as we all know, this was not a normal semester. But so here we have our calibration curve, our standard curve data. And so then plot that data, and we see a curve for the line, or an equation for that line of 0.681 x plus 0.0131 with a pretty decent r squared. And so this is a pretty good standard curve. We also have the sample spot absorption data of 0.827. And so let's just take a quick look at how I then came up with the concentration from that. And so we have, we have an equation of our line of 0.681x plus 0.0131. And this is for our methyl red. And so there's the equation for our line. Now let's just remember this was y equals. Let's just remember what these values are. Remember y is our absorbance. So that equals 0.681 times x, which is our dye concentration, plus 0.0131. Then we can just perform a little bit of algebra to that equation, solve instead for our dye concentration, and that's then going to equal our absorbance minus 0.0131, all divided by 0.681. Some of you are still getting hung up on that algebra a little bit. I noticed in, I believe it was module 3. So be sure that you are familiar with the algebraic steps that I just used to now solve for our dye concentration. And so now what we can do is just take our absorbance value of, where'd it go? There it is, 0.827, and just plug that in. We do this and we find a final methyl red concentration of 1.20 molar. And so that was for our methyl red. We can do the same thing for the malachite green. And so we have our calibration curve for our malachite green. We have an absorbance value at the sample spot. I won't show you that, but it would be done the same exact way. We do that and we find a concentration of 0.585 molar for the malachite green. And so there's our dye concentrations in the river. Now, one of the things that we had to note, and this might have been a little bit confusing for you since we weren't in the lab, so you couldn't see it, but in order to get concentrations that we can actually accurately measure, we had to really concentrate these samples down. And so we took out a sample of the river water, and then using some various lab techniques, we concentrated that sample in order, again, to get them up to values that we could actually measure. And this was mentioned in the lab manual that we concentrated them down by a factor of 100,000. So that means that this 1.2 and this 0.585, which were the concentrations that we just found, those are the actual concentrated values. So now we have to divide each of those by 100,000 to get what the actual concentration of the dyes were within the river. And doing that, we found 1.20 times 10 to the negative fifth for methyl red, and 5.85 times 10 to the negative sixth for malachite green. And so let's record those now and start to just look at the rest of the calculation. And so this is what we're starting with then. We know that the methyl red concentration was equal to 1.20 times 10 to the negative fifth molar. The malachite green concentration, 5.85 times 10 to the negative sixth molar. And so what we need to do is we need to take this information, we need to take the concentrations, match that with what we're given for data for the fish, and we're told that the fish takes in about 100 liters of river water every day. And we need to find out if that equates to a lethal dose or not. Is that enough dye to actually kill the fish? And so let's start with the amount of actual dye that the fish is pulling in every day, or sorry, the amount of water. So we're going to start with methyl red. We'll even switch over to a red color just to get fancy. So we're going to start with our methyl red, and we know that we're taking in 100 liters of water. Now we have to remember what the units of molarity are. Remember, the units of molarity are just moles per liter. So if the fish takes in 100 liters of water, we multiply that by our molarity, and we find that the fish is then taking in 1.0 times 10 to the negative third moles of methyl red every day. Now, we don't work in terms of moles as far as where the calculations are concerned from here on. We want to know the actual amount. We want to know the grams that the fish is taking in. So now we're just going to multiply this by the molar mass. And we can find the molar mass of methyl red pretty easily, honestly. I just Googled it. I found the molar mass of methyl red to be 269.3 grams per mole, which means that the fish is pulling in 0.323 grams or 323 milligrams every day. And so every day this fish, as it's filtering through the water, it's filtering through about 100 liters, which is pulling in about 323 milligrams of actual dye, 323 milligrams of methyl red every single day. And so we want to compare that then to the lethal dose of methyl red. And so for that, what we do is we can look up what we call the Ld50 value. The Ld50 value tells us what dosage is going to kill 50% of the fish that come into contact with it. And this data can be tough to find. When we start to work with environmental sorts of toxicities like this, you might have to take some assumptions and make some assumptions, because as you probably found, you're not going to be able to find the Ld50 value necessarily for fish. The closest that I was able to come up with was I was able to find the Ld50 for rodents, I believe. Where did my... Yeah, there we go. I was able to find the Ld50 value for methyl red for mice equals 3,450 milligrams per kilogram. Now, what that tells you is that, and so if we look at these units a little bit closer, that's milligrams, and I'll actually rewrite it here. That's milligrams of the toxin. So how many milligrams of toxin it would have to pull in? How many milligrams of the methyl red per kilogram? In this case, it was for a mouse, but we're working with a fish. And so this is how Ld50s are reported. It's how many milligrams of the toxin you would have to take in per every kilogram of weight of the organism. We were told in our case, we're working with a 2 kilogram fish. And so we just want to multiply this then by the 2 kilograms. And we find a lethal dose for our particular fish of 6,900 milligrams. And so the fish is going to have to take in 6,900 milligrams of toxin, of methyl red, and 50% of fish, that will be enough dosage to kill it. And so for 50% of 2 kilogram fish, if they take in 6,900 milligrams of methyl red, that's going to be enough to kill them. We can see that our fish are taking in about 323 milligrams per day. And so we can see, and doing some quick rough calculations, and this is where, honestly, we don't have quite all the information that we would need to answer the question. Because we can see that the fish is taking in 323 milligrams a day, but it takes 6,900 milligrams in order to kill the fish. And so it's going to take, it would take about 20 days for the fish to ingest that much methyl red. What we don't know, however, is how quickly the fish can then expel it. And this is one of the other things that must be considered when you're looking at environmental toxicology sorts of issues. If the methyl red is just expelled through the fish's waste, essentially, does the fish pee or poop it out? If the fish can pee or poop out the methyl red quickly and easily, if it takes in that 323 milligrams, does that 323 milligrams come out in waste, in pee or poop sometime through the day? Then the fish is going to be fine. It's not going to be enough dosage to affect it. Some toxins, however, do have an effect that we call bioaccumulation. Mercury is a great example. Mercury is not expelled. Mercury ends up attaching itself to fat cells within bodies. And so it doesn't get expelled in our waste and in the waste of fish. And so that toxins that bioaccumulate build up over time, which can be dangerous. We don't know if methyl red is in that category or not. And so at a best guess here, we could say that methyl red probably is not up to a lethal dose, but again, we don't necessarily know if it bioaccumulates. And so methyl red would not be a lethal dose unless it bioaccumulates, in which case over time, it would build up and then be lethal to the fish. But again, so what I really want to point out is this is not that difficult a calculation. This is one that if you just really sit back and think about it, and this is one of the reasons that, at least in my lecture, I stress dimensional analysis so much. Let the units just carry you through this. Let the units help you figure out the problem. Even if you're trying to, you can't really wrap your head around the science of it, let the units walk you through it, and eventually the science will catch up in your head. Let's look at the same calculation now for the malachite green. And so we know the concentration of the malachite green in the river was 5.85 times 10 to the negative 6th molar. And so we're going to do the same thing. We're going to take our 100 liters of river water times our concentration. And now I'm just going to work in the atomic mass right in the same step. The atomic mass of malachite green, 364.911 grams per mole. Again, let's look at the units here. Liters are going to cancel out. Moles are going to cancel out. And if we remember, in fact, that this was, we can go a little bit further, this was liters per day. We see now what my units would be, and that would be grams per day that the fish is going to ingest. And so we do this calculation and we find out that the fish is now taking in 213 milligrams per day of malachite green. Now the same thing, we want to compare that to the Ld50 value. The Ld50 value for malachite green, and the closest I could find here was the Ld50 for a rat. And the Ld50 value for malachite green is 275 milligrams per kilogram. We have our same 2 kilogram fish, and so a lethal dose to our fish would be approximately 550 milligrams. So that's our Ld50 value for this particular fish. And so again, we can see that every day, the fish is not ingesting enough malachite green in order for it to be a lethal dose, most likely for it to be a lethal dose. Ld50 values are sort of averages too, depending on if there's something different about a particular fish's physiology or metabolism, things like that, then this could be a lethal dose for some fish, but not likely. Because again, remember the Ld50 tells us that 50% of fish who encounter this dosage are going to die. And so it is based on averages. But we can say that most likely this, for most fish, this will not be a lethal dose. So again, we have to consider, does malachite green bioaccumulate, or is it expelled in waste fairly readily? We think about all of these things. But we can see that we're starting to get a little bit closer though with this one, because the Ld50 value for malachite green is so much less. That tells us that malachite green is a more toxic substance than methyl red. It doesn't take as much of it in order for it to be lethal. In fact, it's by a factor, what numbers go? By a factor of almost 10. It's almost 10 times more lethal because it takes less of it in order to be a lethal dose. But again, we're under. And so we can say that most likely this would not be a lethal dose to the fish. However, if it does build up faster than it can be expelled, then it's a concentration which might be an issue. And we just don't have all of that information. So we don't know that for sure. We can only say probably this would not be a lethal dose. And so I hope this helped. Again, one of the big things that I do want you to take home is just the understanding that you can do this. I'll just share a little story with you briefly. I remember once in grad school, I had a class where it was a very discussion-based class, and we talked a lot about the work of historical scientists who came up with some groundbreaking work in lots of different areas of this. This was a class on reaction mechanisms and kinetics. And we talked about the work, and I don't even remember what the scientist was, but we talked about some of the work that he did, which was truly astounding stuff, just phenomenal science going on. And the professor just stopped us for a minute and he said, and we're all first year grad students. I mean, we're fresh out of our undergrad. Honestly, for thinking about where most of you are at, we're about 3 years beyond where you guys are right now. And so not very far in our educations. And the professor asks us, he just stops everything and he says, now, do you think you guys could have come up with that experiment? And we're all sitting there going, well, God, no way. You know, this is a brilliant scientist. He came up with this. We're lowly little first-year grad students. No way we could have thought of that. And he just looks at each other and he goes, yes, you could. Think about what he did. Think about what his steps were. Yes, he came up with some groundbreaking conclusions, but what he actually thought of was not that complicated. He just had to sit back and think about it for a minute. And I share that with you because it's the same thing here. This really isn't that complicated. Look at this calculation right here in front of you. This is not complicated stuff. But the way that it was worded threw a lot of you off. You looked at this and said, I've never seen anything like this before. There's no way I can do that calculation. I have no idea what's going on. And when you're encountered with something like that, your brains just automatically turn off sometimes. And so that's what I really want to stress to you as you go forward. Maybe you're done with chemistry at this point, but if you're going on, or if you're going on in any of your classes, in any of your education, don't let things like this turn off your brain and just shut off. Think about it. Think about what skills that you have and what you've learned and how you can apply them, because this is a very solvable problem. You just have to really think about what's going on and how you can apply the things that you've learned in order to solve it. So anyway, that's it. I do hope that it was helpful for you. And if you have any questions, don't hesitate to reach out. I hope everybody has a great day.